Welcome to the lecture Mathematical Physics. Here is the title of the course, and here is my book for the course. Maybe you found it already in my web page, which is here, because you needed this web page also for theoretical mechanics, so you know it. And there are several materials which can be useful for this course. The first one is syllabus. It is something like that, 2 pages. It is both in Slovak and in English. In English web page, you will find English syllabus, and in Slovak web page you will find everything you need for Slovak course. And there is one more useful material which I will mention. It is only, well, it is mentioned also in the Slovak part of my web page, but it is written in English, and it is something called additional material. I don't remember exactly for this course. Yes, this is something like 50 pages, maybe more. And whenever I discover something that is interesting for me, and something small, which is at the level of this course, not only this course, but also Mathematical Physics 2 and this gauge fields and so on. So I did this computation, and when the computation could be interesting for students also, not only for me, I put it to this material. So it is always in progress, this material, several years already, but it could be also useful for you. For example, if you do some homework, this homework usually is from this book. And so you will find, for example, as a homework, something like this. It is a number of exercise from this book, yes? And if you have a look into additional material, maybe there is something written to this number. Also the page, but the page is referred to the Cambridge University Press edition, not the Slovak. So the page is not very interesting for you, but the numbers of exercises are also there, which are valid also in Slovak edition. So whenever you do your homework, it is a useful habit to have a look to this additional material, whether it is something written to this exercise, because sometimes you can find more like is mentioned in the book. Maybe the most useful way is first do it yourself, this homework, and after everything is done, have a look there. Maybe you will find something more there, that you will learn more, that after your solution you will have a look there, that there is some additional thing to this. So mathematical physics is a very broad subject. So this is the small introduction to this very broad subject, and it is not covering whole parts of mathematical physics even, only this part, which is called usually like differential geometry, representation of groups a little bit, and also differential geometry is some synonym of analysis on manifolds. Is that if you find something called analysis of manifolds, it is something like differential geometry. So mathematical physics has several branches, big branches. One of them is this branch. And in this course, it is only this branch of mathematical physics. For example, there is big branch based on functional analysis. It is a big branch of mathematical physics, and you will find nothing here about this functional analysis. So if you want to know a little more, not more, but a lot of things about operators in general and so on, you should study functional analysis course and not this course. So this course is oriented on geometry point of view of mathematical physics. in physics, usually if we call that something is done geometrically, it means differential geometry, not elementary geometry in plane or something like this. The geometry automatically means that differential geometry. And this course should be some basis for your studying of this geometrical approach to physics. And the course is called mathematical physics, but it is not all parts of mathematical physics. I will start, well, as I told, everything is here in this book, but this book is too big. It is 700 pages, so it cannot be covered in this first course. Only a small part is covered, but it is not so that we will start at the beginning and go to some place and finish there. Yes, I will do it that I will choose several parts of the book by my choice, because I think that for this elementary course it is more useful than just to go for some 3 chapters or something like that. So usually we will start in chapter 2, or also from 1. From chapter 1 we will have something, but maybe on week I will have a look that week 5 or something like that, week 3 will be the concept of a manifold. Manifold is an important concept. It is something where differential geometry actually works, and it will be only on the 3rd week. So first 2 weeks we will do only linear algebra. Yes, you see that maybe you have looked already to this syllabus, and the first week is linear algebra of tensors. It is called complete first week, which is also called that multilinear algebra, because it is not possible to understand differential geometry without understanding of tensors, and it is quite advantageous first to study linear algebra of tensors and only then to put it on manifolds and do some mathematical analysis of this, yes, the analytical point of view. So we start completely with linear algebra. Also some other parts, like for example representation of groups. It is also like here it is just linear algebra, but those parts of linear algebra which probably you do not know for the course linear algebra 1, 2, which usually physicists do have. Now, what is the importance of linear algebra? My favorite citation is Raoul Bott. It is world-class mathematician. I think that already not living, but I'm not completely sure. Who was probably born or lived several years in Bratislava. So it is quite interesting that Raoul Bott is connected to Bratislava. And the interesting thing that he is a very big mathematician, or a very important mathematician, which is somehow connected to Bratislava. And his quotation is that 80% of mathematics is linear algebra. Yes. So if Raoul Bott thinks that 80% of mathematics is linear algebra, this means, for me at least, that linear algebra is extremely important part of mathematics. And you should spend a lot of time on linear algebra because it is worth doing so. Also, linear algebra is very big to study everything. Yes, it is not possible. But for example, for differential geometry, you must be completely sure with some part of linear algebra, and I will do this part of linear algebra the first week, which we need very much to understand for doing differential geometry. Yes, but the linear algebra preparation for many subjects is very important. That first to study what is linear algebra in this problem, and only this, what is other parts of this problem. It is very useful. Also in functional analysis, it is more or less linear algebra, but of infinite dimensional spaces, and it is very non-trivial. It turns to be. So after that, we are already prepared to accept linear algebra first week, because we know that it is important. So what part or what knowledge from linear algebra we need very much? We need, first of all, to understand that what is real n-dimensional, by the way, it is linear algebra of finite dimensional vector spaces only. So we should understand that this will be n-dimensional linear space over R. What does it mean? There is some definition. What does it mean? And you had this definition on your course of linear algebra, that it is a set endowed with some structure, namely that if you have two elements of this linear space, you can do this object, which is called linear combination. Linear combination can be done also from more objects, but if you define exactly this for any v, any w, and any lambda, which is a real number, if you define what does it mean this, you already implicitly defined what does it mean for more terms and more constants. For example, here is constant 1. Think it over, that if you know what this is, you can also understand what is this with k or something mu or something like that. Yes, that whenever we start to construct some linear spaces, we only need to define this guy, and it is enough. That what does it mean here? And if you define this, we want that this should be element of this linear space, and that this has some properties, which you remember from the first year of linear algebra. That, for example, if you here lambda is lambda 1 plus lambda 2, it should be something. Yes? So there are some axioms, and this construction should fulfill these axioms. This is important, and if you don't remember very much what the axioms were, have a look to your copybook from the first year, and remember that what axioms are necessary whenever you speak of linear space. Now, the second thing, there is something like dimension for finite dimensional. It is this number. And this number, by definition, is the number of the maximal number of linear independent set of vectors. So first of all, you must understand what does it mean linear independence. Have a look if you forgot. Second, how many linear independent vectors you have in your vector space. If it is finite number, then also other set of maximal linear independent vectors is the same number. So this number is something characterizing this vector space, and it is called dimension. And we only need real vector spaces. You know that you can define vector spaces over more things like real numbers, complex numbers, finite fields, and so on, but we do not need these finite fields and even complex numbers in this course. We only will study real vector spaces here. Complex vector spaces are very important also in physics. For example, in quantum theory, you will meet complex vector spaces as a very important mathematical stuff. But here in differential geometry, it is interesting only on the higher level. If you know a lot of standard differential geometry for this R, then you can study complex differential geometry, which is also a very interesting thing, but it is not for beginners. It is for guys who already know something about differential geometry. if n is the linear is the dimension of linear space, we always have something which is called basis. So it is a set of linearly independent vectors whose number is this n, any set. In each n-dimensional linear space, we have infinite number of these bases. And what is important, that all bases have the same value for us. There is no preferred basis in a linear space. So if you think, for example, that orthonormal bases are better than other bases, it is not orthonormality, is not property of linear space, but it is linear space plus something, some other structure, something which is called scalar product, and you can norm vectors to 1, and you can speak of orthogonality and so on. In general linear space, this doesn't exist, and this is important to forget structures which are not there. So if I speak of general linear space, I don't speak of linear space plus vector plus scale product. Scale product is additional structure for us, and we do not have any additional structure. So any basis is equally good for us. I will use a shorthand that EA, and this is a number 1 to n. So EA is for us a basis. Now, because the basis is one of equally valuable other bases, then we can go to some other basis. And how it is done? I will write first the formula, and then to explain a lot of things in this formula. So this is n by n matrix. Now notice that in my notation, which I will use here, this matrix has indices whose one of them is upper index and the other is lower index. This is the first fact. Usually, or maybe in the first year, you used this notation. So the upper index on this type of matrices is simply the first one. So the matrix looks like this. These are real numbers in a table, which is square here. Why this matrix is square here, not or just rectangular, but square matrix? Yes, because the number here is A primed. It is a new basis. This was old basis, so-called, yes? And the number of basis elements should be always the same. So this matrix, how it works, this formula, that E1 primed, En primed equals E1 non-primed, En non-primed times this matrix. Check that if you do this matrix multiplication, you can write it in this way. And one more important notice, if you are not accustomed to this, here double B means that it is summation. It is so-called Einstein summation convention. Yes, so for example, this A, B, A, E, B, B, 1 to n. We do not write this because we know that there are two indices, and from them we read that it should be a summation symbol there. It was invented by Einstein, which is a funny thing because it is just a small thing, small simplification of computation invented by Einstein. But because it was invented by Einstein, it is very useful. Yes, it is very big simplification in complicated formulas. So please do not criticize it, but love it. This summation, that it is perfect way how to write formulas without symbols of summation. But it is there. So for example, because here are two indices, it is automatically here means that it is summation. Only after that you have these graphics. So this graphics is in this short formula. This matrix is called change of basis matrix usually. So the name is as it is, the change of basis matrix. And what property should have this matrix in order to be a possible matrix for a change of basis? Sorry? Yes, it should be invertible, because we can go back to the old, if the primed basis is as good as unprimed basis, we can change it in one direction and also backwards. Yes, so that's why this matrix, because the backward direction should be also given by this formula like that, but with some other matrix. And which matrix? Inverse matrix. You can check if it is not clear. So this is not arbitrary matrix, not arbitrary square matrix, but it is square matrix which has inverse, so it is regular. And also one can write that determinant of this A is not 0, which is the condition that the matrix has inverse. So in this part of linear algebra, which we will study now, first week, it is very important to be able to recompute that if I do something in one basis, how it looks like in other basis. And the relation between these two bases is given by this matrix uniquely. If you give me old basis and the matrix, I will give you new basis. If you give me old basis and new basis, I can compute the matrix. Yes, so it is bijection between these objects. And when I spoke about this linear combination, it is very important to understand that what is a linear space? It is a set where you have this possibility to do with objects, linear combinations of objects. And of course, it satisfies these axioms. For example, now there is a maybe nice exercise for you if you do not know it. If you know it, perfect. That imagine that you have two linear spaces and you have two linear mappings, A and B. So recall what is linear map. For example, this A, that if you have two vectors from L1, linear map has the property that A behaves like this, and B similarly. Yes. And now, what is quite useful to know, that whenever you have two linear mappings for arbitrary L1 and L2 within those. So by the way, you can construct matrix of this mapping. Have a look to your copybook of the first year. This matrix in general is not square, but it is just rectangular. It depends on the dimensions of this linear space. But what is important, that now you can define this object, that you can define linear combinations of mappings from L1 to L2. It is defined very simply. So it is definition. What we define here? Define this structure, that what does it mean to make a linear combination of two linear mappings? Now everything is done, you should just check. Is it good definition? You should check that the definition is okay. Yes. So what we try to define a new linear mapping. Yes. If you have two linear mappings, the statement is that this is the third linear mapping, some C. And what does it mean? That the C has to have this property, linearity, first, and second, that this construction satisfies these axioms of what should be true for any linear combination. So I recommend very much to think of this example, that this is an example that we have some set, first, set of linear mappings from L1 to L2. And we so-called make from this set linear space. This is first linear space, this is second linear space, and now we have third linear space, the space of linear mappings from here to here. Yes, it is construction of third linear space. Here is the recipe how to do it, and everything else just check. Everything should be trivial for you, but if it is not completely clear at the very beginning, you should do these checks. In the beginning stage of your knowledge in this direction, you should do as many checks as possible to be able then to do checks in your mind directly. But first do it on the paper, do it precisely, and then when you already will be bored because it is trivial, then not stop to do it and just think yes, it is okay. Yes, I see it. But first you must do these checks. For example, check that this formula is this formula, and so on. Now, there is a very special important case of this, which we will now study, and this will be beginning of the study of tensors. Yes, the first object which we should study is the so-called dual space to the linear. This is given space, and we will construct another linear space. It is space which is called dual space. This is unique construction. So this is our primary linear space, and now we want to define linear space which is denoted L star and called the dual space. So we should tell what are elements in this dual space and what is the way of doing linear combination there, linear combinations. So what are elements? Elements are linear mappings from L to R. So we see that it is a special case of this one. Yes. For L1 equal our given L, and for L2 is R, which is also a linear space. So this is the simplest linear space over R. Yes. And this is our given one. So know that this is special case. So if you prove that all mappings from L1 to L2 comprise linear space, you already proved that this is a linear space as a special case. But I will do it in detail. Not I will not do it, that example in detail. Try to do it yourself. Maybe it will be given for exercises as a homework to be reported by some guy here. But if not, it is very useful exercise for anybody to do it himself or herself. So these are elements of this future space. Now, what is the linear combination? It is given actually by this formula. So here the input is a vector from L, some V. By this definition, it is just alpha on V plus lambda beta on V. At least you should check this if you don't want to do this bigger exercise. So this is really very important. So you should check that this definition makes sense. That first of all, if we call this some sigma, for example, so you should check that sigma is also from L star. So what should it be? Linear mapping from L to R, this sigma. So you should prove that if you have a linear combination, some V plus mu W, the question is whether it is sigma on V plus mu sigma on W. And also then whether this construction fulfills axioms of linear combination. But first of all, whether it is even in the set. Yes. Here, if you prove that from this definition, you will prove that this construction for any alpha, beta, and lambda gives you an element of this set. Yes. And that it is because this set is given by linear mappings. So proving linearity of this sigma means that we are here still after linear combination. Now the natural question is that, okay, this original vector space was n-dimensional. How many dimensions has this vector space? It is either some finite number or some infinite maybe. And a small side note that these infinite dimensional vector spaces, which are the objects for studying of functional analysis, are also very important, also for physicists, because maybe you heard on some subject on electrodynamics and so about Dirac delta function. It is a thing which you already noticed somewhere. So Dirac delta function was a very funny story. That Dirac invented it as a physicist for some computations as a useful tool, and mathematicians do not want to use it because it was for them it was nonsense, because there is no such function with these properties as Dirac delta has. So a majority of mathematicians just rejected this concept that is stupid. But there was a guy who was not so stupid as to reject it, and he thought that how can be that I see that it works. Yes, if it works, it is my fault that I'm not able to do it mathematically correctly, not Dirac. Dirac is not mathematician. I am mathematician. Laurent Schwartz was this guy. Laurent Schwartz came to the conclusion that after some work, that now I know what is a Dirac delta function, that it is not a function, but it is an element of the dual space to the functions, which in infinite dimensional dimensions turns out to be richer than this original one. If this is space of functions, if you construct this space for functions, infinite dimensional space, you discover that it is richer, that there are elements which are here and they are no here, so to speak. Yes? And these elements, which are the difference between the two spaces, are just these interesting things like Dirac delta and similar objects. But we do not delve into this subject. You should study functional analysis, an official theory of generalized functions, so to speak. And here we have just finite dimensional space. And now we prove that if the original space is n-dimensional, this dual space is also n-dimensional. So here, in finite dimensions, it is very simple. The dual space is practically equivalent to this original space. It doesn't mean that it is the same space. They are different spaces, but their dimension is the same. So maybe there are many ways how to prove it, but a way which is useful in itself is that we will construct a basis in this space and then compute simply how many terms has the basis, and we will come to conclusion that n, which is the dimension of the original one. So first fix this. It is in original space. Yes, it was somewhere written that I will use some basis in this L. This means that if you have a general vector, you can decompose it with respect to this basis. So recall that in detail it is this linear combination. These objects are from L, and these objects are real numbers, coefficients of the composition. Now introduce a mapping which is from L to R. That means it looks like our alpha. It looks like element of L dual in such a way that, well, it should be like the picture that if you put here some vector, a real number comes out. This is this mapping. It is so-called crank grinder, this machine, yes? And it is very useful to understand mappings in general. Grinder for meat or for carrot or I don't know what. And now our grinder is called EA, with A something from 1n. So some number 1, 2, 3, 4, but fixed A is now fixed. So if you put a V, it should be some number here. And the number is eighth component of this vector, which is a number. Not all components, but just eighth component. Yes, it is somewhere here, this number VA. But the A is arbitrary, so actually we have no just one mapping, but we have as many mappings, as many dimensions as our vector space. The first mapping, A1, gives you V1 here. The second mapping gives you V2 and so on. Okay? So we have a set of mappings. For each dimension, so to speak, one mapping. So first of all, is it a linear mapping? So if it should be from the dual space, it should be a linear mapping. Now, what do you think from linear algebra? If you have a vector, decompose it to the basis, you have the components, these numbers, and take one of them. And is this mapping that given vector and outside you have eighth component, is it linear mapping? So if you have a linear combination of vectors, and if you compute eighth component of it, is it somehow connected with some components of this original vectors? And what is the exact formula there? Yes, it is. The answer is positive. It is linear. So if you put all these a's to a column, you will get a column of components. Yes. If you have a vector and decompose it, you have this column, the first component, second, and so on. This is an element of Rn. Yes? And now the question is, if you have another vector, some w, you will have column of w components. And if you have linear combination, v plus lambda w, what is the column for the linear combination? And the question is, and this guy has what column?
V1 was lambda w.
Yes, so in each step you do the same linear combination. Here it is just v1 plus lambda w1 and so on. Which is nothing else than the linear combination of these columns. Yes. By standard definition, what does it mean, linear combination of columns? This is the definition. What is the linear combination of columns? In other words, what is the linear combination of elements of Rn? They just do it by components. So here, this fact can be written in this way, that the column which is associated with the linear combination is the linear combination of the columns. It is, I believe, well-known fact. But just the only something like non-trivial fact is to write it to the formula. Yes. But this means that this prescription, that if you put to the grinder the complete vector, and you wait here for this eighth number, eighth component, that this prescription is linear mapping. Yes, because it is from this formula for some fixed a. Think it over. Yes, that if this is true, it means that this mapping is linear for each a. And if this mapping is linear, it means that EA is element of the dual space. So we already have n pieces of elements of the dual space, E1, E2. Notice, by the way, that we use two guys which I called EI. Here it is one of them, and here is another of them. There is a difference, that this index is upper index here, and this is lower index. Why it is so? We finally will come to this, that what is the systematic. But now just notice that if the index is down, it is a basis of L. So I will write it. EA is from L, and EA is from L star, from the dual space, which is a different linear space. And now the statement is that this is the basis of the dual space, actually. That not only they are elements of the dual space, but they are linearly independent maximal number, so it is a basis. How we prove it? That we prove this formula, that if you have general element from L star, general element of the dual vector, and you have these n guys from the dual space, that any general element you can find a formula that decompose it to these elements uniquely. This is the proof that this is a basis, that there is a unique formula for each alpha. So exists uniquely. Now, I will do the proof that this is the case, and after the proof, it means that this is a basis, yes? And if this is a basis, we know the dimension. The number of basis elements is the dimension. So first of all, formulas like that maybe are a little bit tricky, that how to prove that. So what kind of equation it is? What is on both sides of this equation? What type of equation are we going to prove? That what object is here and what object is here? General object now, I mean. Are there numbers, or what is it? Mappings, yes? So yes, they are linear mappings. So the most general, most useful statement is that there are mappings. So we want to prove that this mapping is the same like this mapping. Yes, this is our aim to prove. And if you have two mappings, in general, and you want to prove that these mappings are the same, what is the general strategy to prove that the two mappings are the same? It is trivial, so if you think it trivial, you are right. But what is the strategy of proving that two mappings are equal?
Whether they make the same element or the same number.
Exactly. That the mappings is from some M1 to M2. So put all elements from M2 and have a look whether you obtain always the same element of M2. So put arbitrary V and check whether this is true for arbitrary V. And of course, also arbitrary alpha. We try to decompose arbitrary alpha. We don't know yet what are the coefficients, but whether they exist and are unique, this is the question. So for arbitrary alpha and for arbitrary argument, the question is whether this is the same. Now, here is linear combination in L star, which was defined somewhere. It is maybe already not here. Here it is defined. Yes. So do not forget that this summation over A is a linear combination with coefficients alpha 1, alpha 2, and so on of these guys from L star. So in order to compute the right-hand side, you must take this definition of linear combination of alpha and beta. Here are not alpha and beta, here are EA, E2, and so on, this alpha beta. Think over that using this definition is nothing but writing this formula, alpha A. It is for short thinking. That I do some manipulation here with this expression, and I did it like that V goes here and alpha numbers are in front of this. This is already number, of course. Do not forget that here we prove that two mappings are the same. When we put the arguments to these mappings, we already compare numbers. So we are asking now whether this number is this number, yes? But this number can be rewritten as this number by the definition of linear combination. If it is not clear, check. Now we know what is it. It is VA. It is definition. The proof is nothing but changing of various definitions. Yes. For example, here I use the definition of linear combination in L star. Here now I use the definition of EA itself. It is VA. It is somewhere here. Okay, and what is here? So if this is VAEA, yes, I decompose this vector with respect to the basis in L. Now, alpha is linear. Linearity means that you jump over the constants. Think over if it is not clear. So we have this guy inside, VAEA. We jump over VA, and we have VA alpha on EA. Because of the definition of something. Definition of that alpha is a linear mapping, and the definition what is it, a linear combination with respect to the basis in L. So now we have to compare whether this and this is the same thing for any alpha and any v. If v is any arbitrary, yes, so it can be only true if this is, well, is this. Then it is clearly true. So we have that, first of all, it is possible to write it like that, and we already know how to compute this alpha a, these coefficients. Put to the complete alpha basis in L. Yes, so we see that, yes, it is true if you put alpha a equal alpha on EA. And this is unique. So first of all, we can find these numbers. We wanted to prove whether there are numbers here to obey this equation for any alpha. We proved that, yes, it is possible. And here is the prescription how to compute these coefficients. And this prescription is unique. So the answer is that this is true. Think it over. It is very simple proof if you think it over properly. But for the beginning, you must somehow start to think in this way, in linear algebra, which you need for differential geometry. That proofs like that should be easy after some time for you. Maybe on the beginning you are not accustomed. I don't know. Maybe you are accustomed and everything is trivial for you. It is perfect. But if not, just sit down, study every step, and you will see that after several hours, maybe you will be prepared to do proofs like that very easily. Yes? Because they are really very easy. You just have to remember several definitions. What is the definition of alpha, of this element in L star? It is linear mapping from here to here. What is the definition of linear combination there? This is the definition, and so on. Maybe 2, 3, 4 definitions, and just combine, nothing more. There is no need to be any genius for these proofs, just combination of definitions, nothing more. So the complete generality is to remember several definitions here. So now we discovered already that, to summarize, that for each n-dimensional linear space, you have a new linear space called the dual one, whose dimension is the same one like the original one. The elements are linear mappings from this original L to number, which is also a linear space, the simplest one. And we already found a useful basis in this dual space, which, notice, is somehow glued to the original basis. You cannot construct the new basis if you do not know the old basis in L. Yes? So in L, you should fix this basis, and then you can compute this basis in the dual space. So the second one cannot exist with without the first one. It is uniquely given in this way. It is very important type of basis in L2. Of course, you can use any other basis, but this is the most useful for you if you use this basis in L. And it is called the dual basis. This is some basis. This is the dual basis. Now, usually it is written in a simpler way. Well, here it was that EA on V is VA, yes? If V is VA EA. So here you see that you cannot tell what is VA if you do not know what is the basis in the L. If you fix basis in L, then you have components in L of any vector, and then you use these components as the answer, what is this value. Now, give a special case, V equal EB. EB. So take eighth element of this basis and put inside bth element of the original basis. You can, because you can put inside any vector from L. So in particular, you can insert that there your basis. So what we get? If this is for any element, what is the result here? And why?
Because we get zeros everywhere else, just the one.
Yes. So here should be eighth component of this vector. Yes. But this is basis vector, so its components are all zeros except for the number b, where it is 1. So here is delta AB, which is Kronecker symbol, number 1 when A equal B, and number 0 if A is not equal to B. Yes? Now imagine that the definition would be like that. Remember that if you want to define a linear mapping, if you know that this mapping is linear, the complete description of this mapping is given if you know what is the result of the mapping of the basis. If you know where basis goes, you know where any element goes by linear mapping. Do you know this fact from this first course linear algebra? Do you remember something like that? That any linear mapping is uniquely given on mapping of the basis. Yes? You can construct the matrix of the mapping with respect to this basis and with respect to the basis in the second linear space. So this is linear mapping. So we know that if we define it on basis, it should be everything. We do not know any more information. So we can construct from this formula, we can go here. Also, now we went from this formula down. Yes? My way of description that first defined it for any vector, and then as a particular case defined it for the basis. So I did it in this way. But your knowledge of linear algebra should give you that also it can be also vice versa, because this is linear mapping. So if I do it on basis, it is everything. I don't need anything. I just need to remember the way how from the basis I go to arbitrary vector. Think it over, and after this thinking over, please have in your mind that this and this formula are completely equivalent. Yes. So this is one definition of this guy, and this is another definition of this guy. Completely equivalent. And now I will change the notation to the one which is usually used in this stuff. Namely, that this is a number. When we insert a vector v into this element alpha, this element from, this is from L and this is from L star, we get this number by definition. Yes. Now we will denote it differently in this way. That's this type of brackets. It has some advantages, and it reflects an important property of this number, that actually this is something like, this is called, this object is called bilinear pairing. Bilinear pairing. And what is this machine? It has two inputs. Put here alpha and put here v. And here you obtain this alpha v. So the name of this machine is this one. It has two inputs and our output, which is a real number. So of course also the left-hand side has this property, but here it is stressed, this fact, that actually we have a type of bracket which is a bilinear mapping. This guy goes from L star and this guy goes from L. Now we will come to it, but you remember, sure, that what is a bilinear form from linear algebra? Do you remember that in second semester of linear algebra you have bilinear forms? Is this a bilinear form or not? You think that yes? So how many of you think that this is a bilinear form? And is there anybody who thinks that it is not a bilinear form? So the answer is that it is not a bilinear form. It is more general object. And what is the difference? Do you remember what was the definition of the bilinear form? That what are inputs in bilinear form? Vectors, yes, two vectors, but these vectors are from arbitrary spaces or from the same spaces? The same space. The bilinear form needs arbitrary two vectors from the same vector space. And notice that here are vectors from different vector spaces. So that's why it is not a bilinear form. It is more general construction, which is called bilinear pairing. So bilinear form is a special case of bilinear pairings. Maybe you remember, we will come in maybe next lecture to these bilinear forms as a special tensors. And you remember that to bilinear form in a basis you can assign a matrix which is square matrix, because the vectors are from the same vector space, this is, the resulting fact is that the matrix is square. Here, these vectors also come from the same number of spaces, of the dimensions. So if we assign a matrix to this, it can be done. We also obtain a square matrix. But in general, if you define a general bilinear pairing, this is a very special bilinear pairing. This bilinear pairing is called canonical bilinear pairing. Here, canonical. This is the word which is rather dangerous for us, very important, and the official definition, as far as I know, needs category theory, so I will not go to that in very strict definition. When we come to the place where this word will be really important, I will say some practical definition. What does it mean canonical? That something is canonical, something not. So here, the general bilinear pairing can have any vector space here, including not the same dimensions. And then the matrix of this general bilinear pairing can be non-square, just rectangular. But here, this canonical is not a bilinear form because the vectors are from different spaces, but still the matrix is square because the dimensions of these vector spaces are equal. Yes? So this notation reflects better that, for example, that we have also linearity in this alpha. Here it is not clear that this expression is linear in alpha. By the way, linearity in V and linearity of alpha, which here is very explicitly written, has completely different reasons. Linearity on V is the result of definition that alpha is linear mapping from vectors to real numbers. And linearity of alpha is definition how to make linear combinations in the space of these mappings. So they are thinking over that there are completely different reasons for linearity of this number with respect to V and with respect to alpha, but the linearity is there. Independently V, independently alpha, and that's why this notation is somehow more instructive, that it reflects this bilinearity of this object. So from now on, we will use this notation for this old object. And the bilinearity means that if you have alpha plus lambda beta here and V, it is alpha on V plus lambda beta on V. Yes? And linearity on V is that for fixed alpha, V plus lambda W is alpha on V plus lambda alpha on W. So this is the bilinearity of this number. There are two independent linearities at the same time. But in spite of this, this is not a bilinear form. Yes? It is a pairing. So what next? You already know. Now, perhaps this is useful. What's the time? Still 20 minutes. So first of all, we can study how all this behaves with respect to the change of basis. So let's have this change of basis. Given by change of basis matrix A, general. General, I mean general invertible, of course. Then the question is, what happens with the dual basis? The dual basis should also be a new one, changed. Why? Because the dual basis is uniquely given by the original basis. We came to this conclusion that whenever you fix basis in L, you have fixed already basis in L star, which is called the dual basis. So when you change the original basis, also the new basis should be changed somehow, but we don't know how it is changed. But it also should be changed by some change of basis matrix. So let's call the unknown matrix B. This is the formula that, well, this is primed A. But upper index, this is change of, so this is given, and this is unknown to be computed. And how we compute very easily if you take into account this formula. This formula in the new notation, by the way, in our new notation, this formula is like that. So this formula says that the left basis is the dual basis to the right basis. Yes, it is this definition. Now it is a little bit tricky that this looks like something else. It looks like what, this formula? Especially when it is written like that. What is it similar to, this formula? Scalar product. And when it is the scalar product, then this formula says what? It is orthonormality. Yes, exactly. Yes. So the danger of this formula that you should think that it is the orthonormality condition for your basis, but it is not the case. It is not orthonormality, because orthonormality is in one linear space. You should have scalar product and formula something like that. Yes, for example, something like scalar product of EA in B is delta AB. This is the condition of orthonormality. We will come to that when we study tensors, because it is actually something with tensors. But this is not orthonormality condition. It is condition with respect to basis in two vector spaces. First of all, L, and the second one, L star. It is not orthonormality. This basis is arbitrary. Yes? You even cannot speak of orthonormality because you do not have scalar product in this L. So it cannot be orthonormality condition because you have no measure to do it. So first warning, this is very important formula, and it is not formula which says that the basis is orthonormal. Yes, it is completely different meaning. Now, we change the original basis. We get a new basis, and we also want to construct the dual basis. That means given by the same formula. So we have original basis. This is a dual basis to the original one. Now we have a new basis in L, and this is the new basis which should be dual in the dual space. And the question mark is, what is this guy? So we want to compute the new dual basis. So just compute. Insert these primed objects like here. So here is B, A, C, E, C. It is, of course, summation over C. Yes. Here you have A, B, D, E, D. So I inserted the prime objects in terms of non-primed objects given by some matrices. This matrix S A is given, and this matrix B is to be computed from what is needed. Now, this is bilinear machine, yes? Put here something, and it is linear with respect to this slot and linear with respect to this slot. What does it mean? That all numbers jump out. So this goes out, and also this goes out. Altogether, B, A, C, A, D, D, these are the numbers which jumped out. And what left inside is E, C, E, D. And what it should be once more delta AB. Because we want a new dual basis. Now, this is old basis and its dual basis. So here should be delta CD, because the first basis here and here is already dual. This is assumption. Now, CD means that you should sum over this CD here, and of course delta goes away. So it is BA, for example, C, ACB, that's all, and this is delta AB. So this is the equation from which we should obtain this B matrix. And what is written here? It is some manipulations with, this is one matrix, second matrix, and what is done with matrices in this equation? They are multiplied, yes? So because here is C and here is C, it is multiplication of matrices. So it is what? It is that BA as a matrix is matrix which is that, and it is unit matrix. Yes? So we see that B is A2 minus 1. So we have already quite important result that whenever you mix your bases in terms of the change of basis matrix A, your dual basis is already automatically mixed by the inverse matrix, not any other matrix but inverse. So here is E primed. Now, imagine a vector which is decomposed first with respect to the old basis and next with respect to the new basis. So the same vector is decomposed first time and second time with respect to the old basis and new basis. Yes. So we have two columns assigned to this vector. This is the column of components with respect to the first basis, and this is the new column of the components with respect to the second basis, which is arbitrary. So this is now A, B, E, B from here, the new basis. So if we take this guy, what is it? If the vector can be written like that, what should be this object here?
The new from parts.
This is the old basis. It is not, here is primed, so this is what? It is like here, but just use the letter B instead of A. So here it is A, but it also could be BB, yes? Because it is just summation index. And if here you have BB, it is also the same EB like here. So this should be what?
Equal. I mean, with some deltas in there.
But if this should be this. What should be this guy here? VB, yes? In order, VB, EB, VB, EB, it is the same, yes? Okay, so write down explicitly, VB is AB, A, VA primed. What we want, primed V in terms of the old, unprimed. So what is VA primed from this formula? It is e to minus 1 A B V B. This is matrix multiplication. This is the column of old V's. It is a matrix and it is a column of new V's. Yes?
We see already from the first matrix multiplication that B times A in the matrix plus 1
Yes. Yes, we can use also this.
If matrix times B.
Yes, you can do it in many ways. I did just one way. You can invent your private proof, which will be different. It is very useful. Yes, I recommend to do it. Whenever you see my proof here, do yourself your better proof at home.
I was just so weird because I thought it was done new and recently because there's something.
Well, it was not yet done on this lecture, at least. Yes, so it is so important that I had to do it. So what we discovered this formula. So take these two formulas, that if you have a vector and you change your basis in terms of matrix A, for the fixed vector you also have to change your components, because they are components with respect to new basis. Yes? And what is the formula for the transformation of components? It is this formula, which uses inverse matrix. Yes, inverse matrix. So I will try to write it graphically, that E goes, or in detail, E1 goes to En, goes to E1 primed, En primed, which is the old basis times the matrix A. This is this definition of the connection with primed basis and unprimed basis. Yes, it is graphically like that. Then V1 and Vn goes to V1 primed, Vn primed equal to A to minus 1 applied to the old one. So this is graphical version of these two formulas. That if you change a basis with matrix A, you should also change the components, but with matrix A to minus 1. It can be directly or visible that here the matrix, if you insert here somehow this, I think A minus 1 or maybe vice versa, you will obtain these formulas. Yes, that you can do it somehow inserting this unit matrix in the middle here, these two formulas. But it is much simpler to do it explicitly. Yes, and then also read it graphically, that I obtained this formula. What is it graphically? Graphically, this formula is like that. Now, new computation, what happens in the dual space? We already know what happens with the basis. Yes, we know that the new basis, the new dual basis, is given by inverse matrix, the old dual matrix B, sorry. Now, imagine you have an element of the dual. By the way, definition, the elements of the dual are called covectors. Yes? So this is a covector. And vector is from original space. So when I say this is a covector, it means that it is element of the dual. Co is from Greek, I think. It is something like together with. That this vector goes with this vector somehow automatically. That's why it is called covector. Now, imagine we have a covector, alpha, element of the dual, and we have the proof, here is the proof, that it can be expanded with respect to this dual basis. But also it can be done with respect to the new dual basis. Yes? Similar computation, what we want to know, what are these numbers if we know these numbers and these metrics. So this matrix says us what is the relation between old basis and new basis. And now we want the components, relation between components of a given covector. Yes? So just compute. This is B, so A to minus 1, A, B, E, B. Then put it B instead of A. So I will do BB, because here is EB. What does it mean? That this guy should be the same like this guy. This. So I write it, alpha B equals A to minus 1 B A alpha A primed. But it is inverse formula with respect to what I want. I want prime in terms of unprimed, so I inverse it. And I come to A, B, alpha, B. What is the graphics here? It is alpha 1 primed, alpha n primed is non-primed multiplied by a matrix A from the right. So not columns, but how is it called, this column and rows, yes? Okay, so this is all for the first lecture. For the next lecture, please read everything what was here, because perhaps it is a little bit new for you, and you must be accustomed to this way of thinking. It is not complicated, but I don't want to add anything for the first lecture, just to be prepared for the second lecture. Yes.